Hello. So today we're going to work on a particular problem. We're going to call that a combined problem. You can also call that a two-stage problem. So you have typically a conservation of momentum. And then you follow that with conservation of mechanical energy. Okay, so let's give this example. So let's say if I have kind of like a pendulum and has a little mass, or a block, okay? So that's the block, and the block is equal to, say, 1 kilogram. Right? And then you have a bullet. So this bullet, let's say it's 10 to the negative 3 kilogram, which is equal to 1 gram. And it's shooting at this block. So let's assume this time that travel from here to here, this delta t is very small because it's very fast. So let's say the velocity of this bullet, let's just call that V1. It's equal to 10 to the 2 meter per second. Okay. So now the question asked, so let me change in color. Question asked, how high would this go? Okay. So let's say finally he is somewhere here, the block. So then we say, how high did it travel? So we're looking for this h is equal to what? So we know also that the bullet went through this and then it comes out, okay? So I'm going to draw the bullets comes out. The bullets comes out and slow down a little bit, or not a little bit. So the V1 prime, let's say, is equal to 10 meter per second. So it slowed down quite a bit. All right, so in this scenario, what would be this mass new height with respect to the original position right here? So that's the h you're looking for. So also, that's one thing you're looking for, but the other thing, so the question you're asking for, A, so what is the V, so let's call this one M2, okay, M2, and call this one M1. So what is V2 prime equal to, okay? And then what is H equal to? So that's the question. So how do we formulate this problem, right? Okay, so let's give it a little space right here. So we're always looking at formulation, right? So formulation is what's important. Okay. So we're going to break this problem into two-stage type of problem. So first, the bullets, let's say it takes very little time to go through, okay? So obviously, the bullet goes through here, it's going to generate some heat inside, and it's going to create a hole, right? A hole, and then comes out, okay? So it takes very little time. And so we're going to assume there is a collision problem here, right? So right before this bullet, when this bullet is right here, the velocity didn't change. There's no air drag, so the velocity is still v1 is equal to this one here. So right before, so that's important to realize. Right before this is just v1, and then right after the collision, right? So right after the collision, we have this v1 prime equal to 10. So it's right there, okay? So there's not much of a change there. So this is right after collision. Okay, and this is right before, right? This is right before, and it's also right. This is right before collision. Immediately right before or immediately before collision. So you can see from here to when this one just come out, there is a problem there. There is one type of problem that's involved right here. And from here to here, right? So from the bullet before it enter and right after it just come out. So this one here is the conservation of momentum problem that we can formulate, conservation of momentum. Okay, so that's stage one. So I'm going to call that stage one. And you have conservation. I'm just going to say conservation of momentum. I'm just going to short the COM. Okay, so I'm going to call that a conservation of momentum, right? Conservation of momentum problem. All right. And so in order for that to be true, obviously we need to know that net force, right, in the x direction. So I'm going to draw the axis right here. So axis, let's call this one here is x direction, right? So in the x direction, that's where we care, because the collision happened right at the bottom and it's all in this direction right there, right? So in the x direction, right, in the x direction, this net force is equal to 0, right? So is that true, right? So at that position, right there, you have mg and t. If it's not is resting, mg and tension cancel, and the only thing that could give you the net force in this direction is your drag, right? But once you enter it, there is force between these two, but your system is the bullet and the block, right? So keep in mind your system is equal to bullet, right? So it's that, right? Plus the block, okay? So then this block is resisting, right? Or it's pushing the bullets, and the bullet's also pushing the block, and there's going to be heat inside the block, but that is all internal forces, so we don't have to worry about that. That's not considered part of the net force, which is typically external, right? So these are external. Okay, right. So that's important to realize. So we have stage one, and then we have stage two. Okay, right, stage two. What are the stage two here? So stage two is afterwards, this bullet comes out, and now this block receives some velocity, and he's going to keep swinging, right? He's going to swing up like that to that position, okay? So that we're going to formulate as a conservation of mechanical energy, right? So for that to happen, right? So it's a conservation of mechanical energy, right? So for that to happen, we know that your conservative work need to be 0, right? The work done by the conservative force need to be 0, okay? All right, so let's see. So we have stage one and stage two. So now we're going to erase this here, and then we'll continue. So we're looking for the V2 prime and the height. Okay, so let's erase this. Okay, so stage one. So stage one, we say M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V2 prime, okay? And M1 is equal to 10 to the negative 3, V1 is equal to 10 to the 2 plus M2, which is equal to 1, and then V2 is 0, initially at rest, and that's equal to 10 to the negative 3 again, and this one here is 10, and then plus M2 is equal to 1, and then what is the V2 prime? Okay, so you can find the V2 prime from here. So let's just do that. So 10 to the negative 1 right here, and then minus this one here is 10 to the negative 2, right? Minus, so minus 0.01, right, is equal to V2 prime. So V2 prime is equal to 0.09. okay, or 9 times 10 to the negative 2 meter per second. All right. So that's v2 prime. So the blocks have velocity immediately after. Okay, so we find that. And then now we're going to do the stage 2 problem now. So stage 2 problem says that, okay, I have this, so I'm going to write 0, right? It's going to be equal to the change of, no, I'm just going to write, so I'm going to call this position 1 and then call that position 2, okay? So I'm going to have mechanical energy 1 is equal to mechanical energy at position 2. So then I have PE1 gravitational plus KE1 is equal to PE2 plus KE2, okay? And I know it comes to rest right here, so I know KE2 is 0. And I'm going to assume right here, this is my reference, right? It's my reference for the gravitational potential energy, right? Potential energy, gravitational potential energy. So that's 0. So I'm going to call this one 0. Okay, so now I have 1/2 m v2 prime squared equal to m g h, right? So that's what I have. So I'm going to change in color here. And now I'm going to cancel m. Okay, so we can find h now. So h is equal to 2g, right? So I'm going to divide g over. And then I have the v prime, right? V prime, oh, sorry, v2 prime, and then square, right? So that's that, right? That's what I have. So then you're going to put that in. So that's 9 squared times 10 to the negative 4, right? I'm putting this one here over there, and then divide by 20. Okay, so you can do the algebra yourself, and that will come out to be in a unit of meter. Okay, so that's what we have today, and hopefully you get to apply your two law in this problem.